Greetings and welcome everybody to Chapter 2, Lesson 2-6, Ratios and Proportions. So today's learning targets are as follows. We will be comparing ratios. Also, we will be solving proportions. Some good stuff in here today, guys. All right, now how do we know that we're going to be successful? Well, simply put, you, me, I will be able to determine if two ratios are equivalent by finding common denominators and evaluating cross products. Also, I, we, me, you, we will be able to determine one unknown value which makes two ratios equivalent by finding common denominators and evaluating cross products. A lot of good stuff today, guys. So keep the following questions in mind as we proceed forth on our journey toward mathematical enlightenment on the high seas of this mathematical course. So, one question to keep in mind is what must be true about the units in the numerators and denominators of ratios in a proportion? Units, very important to keep that in mind. Is there more than one way to set up a proportion? How can you find a unit rate from a given rate? All this and more will be answered today as we go forth through the lesson. So let's not waste much time. Without further ado, here we go, guys. Let's roll here. All right. So, first thing to understand, all right, we're talking about ratios, we're talking about proportions, and essentially what they allow for us to do. So, ratios allow us to compare many items by using a common reference. We'll talk more about that, what that means specifically, but I like to illustrate concepts. And so I'm going to illustrate the concept in the table below by showing, let's just say, for example, the number of restaurants for a popular fast food chain for every grouping of 10,000 people in each of the identified countries below. You can kind of see it a little bit here. I'll scroll down here in a second. We'll talk more about it. Okay, so in this case, the quantity being compared is the number of restaurants, and the common reference is the grouping of 10,000 people. Okay, so let's look at this a little bit further, guys. Let's look at this a little bit further to understand what's going on here. Let's look at my table here that I've put together. Okay, so here's the table. Once again, you've got a list of countries: US, Canada, Australia, Japan, United Kingdom, and Taiwan. And they all have the number of restaurants. So that's what these are, these decimal values. The number of restaurants for each grouping of 10,000 people within the country. So you can see US 0.413, Canada, Australia, Japan, and so forth and so on. So what that means is that, again, zero point 0.4, almost a little less than half of a restaurant for each 10,000 grouping of 10,000 people in the country of the US. For example, that's how you interpret these things. So before we get further along here, let's understand how ratios can be represented. There are many ways they can be represented, and we'll talk about a few ways. The first representation, believe it or not, is in fact through this table. That is representation number one. For you see here, I have a value here, and this labeling tells me that this value is in relation to that value there. Believe it or not, a table itself is a representation. But let's talk about some of the more common representations you will see, especially, well, just in life in general, but especially even those that you'll see when working through problems. So a couple representations. This is by no means the most exhaustive list of representations, but this will get us going. So let's just focus on one of these countries. This one just happens to be the first one listed. Let's just focus on that to help illustrate the different representations. So you'll see ratios sometimes represented as this. You'll see, I'm gonna use a variable first before I start putting numbers together. So let's say that we have one value, and you'll see this little colon symbol here, and then the other value, or in this case, like I said, I'm going to use variables to illustrate the point before I start putting numbers together. So when we look at the US, the situation here with the restaurants and the 10,000 people, what this would end up looking like is something like this: 0.413 compared to 10,000. Well, hold on, that's too many zeros. There we go. There we go. Okay, another representation that you'll see is something like this: x2y. There you go. X2, literally the word 2 spelled out. X2y. And it would look like this. There you go. 0.413 to 10,000. And here's what we will most commonly see, and the one we will most commonly be working with in Algebra 1 and really beyond, especially mathematically speaking. But here's what we'll use, right? We'll have a value, and it will be in a fraction related to some other value, uh, and there's a numerator, denominator, one of them, both of them, right? This is how it would look, right? Point 0 or 0.413 compared to 10, again, too many zeros, 10,000. Right, this is what you'll see most commonly is, like I said, in math, we will be working with fractions. Fractions are very scary things at times. They are the nightmare fuel to many up and coming mathematicians. And the more engaged we are with our demons, the more we are able to slay our demons, the greater good, the greater path to redemption that we shall take. If that makes sense. I don't know. But regardless, what I'm saying is that fractions are going to be a thing. We need to get very comfortable with the fractions. All right, guys. So let's think about some things here. Okay. So suppose, now keep in mind, this was a relation of restaurants to 10,000 people, each grouping of 10,000 people. But what if? What if I wanted to say, you know what? How many restaurants are there for groupings of 100,000 people? What would I do? What would I do? What would I do? So let me think about something for a second. Well, this is starting to sound very math problem-ish. So I'm gonna use my commonly known math representation for ratios here, and I'll say x is, I'll say it's, I'll say it's the number of restaurants per 10,000 and per 10,000. There we go. All right, I'll kind of set it up like this. Now the question is, okay, this is 10,000 people. How do I want to, I want to understand how many restaurants that may serve 100,000 people. Well, let's see here. Basically, what you might want to consider is applying some mathematical properties that you may be very well familiar with at this point in time. And let's see here. If this one you may start getting the alarm bells going off when you see what's about to happen here, okay guys? But here we go. Let's assume here now. Remember, if I have any number, I'm going off on a tangent here, guys. I'm going off on a little tangent. Let's say I have a little or any old number here. Let's say the number 5, and I multiply it by the number 1. Well, the result is still itself. It's 5. It is the original thing. It's still itself. Thus, if we manipulate mathematical expressions and equations by multiplying things by the number 1, then that appears to be a valid mathematical application that we can do. So perhaps I can get some sense as to the question here, each grouping of 100,000 by multiplying things by the number 1. So let's see here. If I wanted, let's see, here's people, and here's restaurants. And let's see, I wanted my number of people to go from 10,000 to 100,000. Again, people. And let's see here. Well, in order to go from this number to this number, you might recognize the idea that there would be a common denominator, the least common multiple, in fact. Let's see if I listed out 10,000 and another 10,000 would be 20,000 and so forth and so on, right? I could do that, and basically the least common multiple here would end up being 10. 10. 10 would be my least common multiple. That would get me from 10,000 people to 100,000 people. And if I represented that 10 um, as a representation of the number 1 here, so let's see, let me just go ahead and make it very clear. I am using the identity property of 1. And that property basically, like I just said, it states that any number times the number 1 is itself. And so I can use that knowledge, as I said before, to make valid manipulations of expressions and equations that is within mathematical law. It is within mathematical law to do so. So that's what I'm going to do here. It doesn't change, multiplying things by 1 does not change the balance of an equation, so I can simply say that, so I don't have to do it to both sides, I would simply do it to this 1 here. So anyways, not to get too mathy on you, but basically times 10,000 people by 10, you get 100,000 people. Right, you see how that works, right? Multiplying fractions, multiply the bottoms across, and you multiply the tops across. So 0.413 happens to equal 4.13 restaurants. Okay, all right. So what does this all mean? What does this all mean, guys? What sort of enlightenment can we ascertain from this? Well, basically what I'm saying is that since we are able to apply this property, we are thus then able to say that thus we are then able to say that 0.413 restaurants compared to 10,000 people is equivalent to is equivalent to 4.13 restaurants for every 100,000 people. Why can we say it's equivalent? Because all we did here was simply multiply by 1. Again, anything times 1, and 10 over 10 is a representation of 1. It is, so 1 equals, 1 over 1 equals 10 over 10. All right, these are all different representations of the number 1. And again, according to this property, whatever we multiply by the number 1 is itself. So we multiplied this by the number 1, and this was our result. It is itself. Itself is equivalent to itself. Thus, 0.413 restaurants per 10,000 people is equivalent to 4.13 restaurants for every 100,000 people. So the idea here is that when two ratios are equal, which is what we have here. That's the scenario that I've sort of laid out here. When we have two ratios that are equal, it is called a proportion. This is a very key thing that we must understand, for this is really the value of this whole lesson here is proportions. And in life, we will use proportions a lot in problem solving. And properly setting up a proportion requires the numerators and denominators. Let's see, denominators between the two, so the two being the two ratios, between the two have the same units of measure. So in other words, if this isn't clear, what I'm saying here is that I have two ratios, okay? And I was very particular to set up that this denominator of people is also going to equal, I made sure that people was on the denominator, or they could have been on the numerator, but the point here is to say that wherever people is in this particular ratio, whether it's here on the bottom or here on top, when you equal it out to the proportion, it has to be in the same spot. I couldn't have this right here. I could not have this right here. This is what you cannot have. You cannot have 100,000 people to 4.13 restaurants. That is a no-no. You cannot have that, right? They have to be on the same, right? If this one's here on the denominator, it has to be on the denominator too. It can't be across like this. That there's just no sense in that. You just can't do that. That's not in line with the idea of proportions. So be very particular to when you set up proportions to keep them all on the same, like whether they're numerators or denominators, keep them the same wherever they are. So, and then 100,000 people. Okay, so makes sense. Let's try some. Let's try some problems here, guys. See if that makes some sense here. Now, on these next couple of problems here, I want to just understand, are these equivalent? Just like what we did up here. We we took we took a ratio that was given to us, and we did a little bit of manipulation to get some other results, and we determined that they indeed were equivalent by using this property here. So I want to sort of gain the same idea. Are they equivalent? Well, let's see here. 2/3. Let's see, I'm going to set up my 2/3. Okay, I'm going to set up my 2/3 like that, and I'm going to pose the question, well, are they equivalent? Well, let's see here. If I want to go the least common multiple approach, get common denominator sort of approach, let's see. What I would say, I have 3, 6, 9, 12, 15, 18, 21, 24, and then I have 24, 48, right? The least common multiple appears to be 24, right? That's the least common multiple, least common denominator, however you want to phrase that. So, and it took me 8, I just erased it here, but you will have noticed it took me 8 listings to get to, let's do this, make sure here, 1, 1, 2, 3, 4, 5, 6, 7, 8. It took me 8 listings to achieve common multiple. So that is the link here. That is the link that I am going to use here. I am going to say that if I multiply this by a denominator of 8, and not just a denominator, but I want to take advantage of that identity property of 1, right? I want to take advantage of the identity property of 1. So I want to have a ratio all unto its own of 8/8. I want to multiply this expression, this fraction by 1, and see, is it indeed equivalent to this here? It's posed up here. So let's try it. Let's see here. Let's see. 3 times 8, that would be 24. Let's see, actually, I'm going to go ahead and do it like this. Okay, so I'm gonna set it up just like this. So let's see here. If I do just that, Let's see, 2 times 8 would be 16, and 3 times 8 would be 24. Now the question is this equal to what was up here? Let's see here, let me set it up here, 16, 24. So I'm saying I'm going to take this, move it over here, and I'm going to take this and I'm going to move it over here. Now my eyeballs are sort of directed over here. Are these two things equal? Question mark. Well, it looks like I got a 16 over 24 equals a 16 over 24. That is indeed true. They are equal. They are equivalent. Thus, we proved it. We took advantage of the identity property of 1 to obtain common denominators. And that method there tells us they are indeed equivalent. All right, well, let's try this other one here very similarly. Very similarly. So let's try here. Let's see here. I'm going to do 2/5. And let's see, if I'm looking at this one here, I can list out 5, 10, and this one here, 10, 20, 30, and 15. And they appear that the least common multiple between the two, right, here's the 5s and here's 10s. The least common multiples of these two values happen to be 10 themselves. It took me two place values, or two listings, I should say, to get to 10. So, in other words, I have found my common denominator, right, my common link here to be 2. So, I'm going to put that on my denominator. I'm going to also put it on my numerator. Thus, I am multiplying by a form of 1. Thus, I am in complete compliance with mathematical law, and life's good. So let's see, 2 times 2 would be 4 over 5 times 2 is 10. That's that there. Now, the question becomes, is it equivalent to this thing here? Let's see here if I write it out. Okay, now the question is, all right, I got these two things here. Okay, are these equivalent? Question mark. Well, let's see here. I got 4 over 10 equals 6 over 10. I mean, those appear different. A 4 is not equal to 6. The 10s are good. The 4 and the 6 are not. Thus, the question here, it's false. These are not equivalent. All right, makes sense, guys? Let's tackle the next one here. Tackle the next one, 1/6. You notice I'm sort of, my pattern here seems to be I'm going to manipulate the one with the lower denominator into trying to match the higher denominator somehow. So that's sort of the pattern I'm starting with, if you've noticed what I'm doing here. But anyways, let's see, I'm taking my 1/6, and let's see, I can again, if I take the number 6 and list out the common multiples, same with 30, I will get, 6, 12, 18, let's see, 24 and 30. Let's see, it's okay, 30 right there. This one starts at 30, 60, 90, etc. Well, I see a common link here, 30 and 30. It took me 1, 2, 3, 4, 5 positions, 5 listings to go from 6 to 30. And when I took those 5, it got me the common denominator. So what I'm going to do here, folks, is multiply, is set up a ratio unto its own of denominator 5, but I want to take advantage of multiplying by 1, so I will set up the numerator to also be 5. Whoops, hold on a second here. There we go. Okay, there we go. I set things up here. Okay, let's see, equals, or no, not equals, but let's say, this is my arrow here. Okay, 1 times 5 is 5, and 6 times 5 happens to be 30. Now, the question is, see if I took this and I got that out of it. Whoops, I took this and I got that out of it. Now, is that equal to this thing here? Well, let's see here. Let's see, 5 over 30. Question mark? Are these equivalent? Let's see. 5 over 30 equals 5 over 30. It does. They are the same. They are the same. So thus we have true. It is true that they are equivalent. Yes. Not too bad, guys. Again, this is a very nice, neat trick. You're using common denominators. You're applying the identity property of 1 to determine if in fact they are equivalent ratios. Right? You can then write, let me be clear here. You can, at the end of the day, say 2/3 is indeed equal to 16/24. At the end of the day, you can indeed say Actually, not this one here. This one was false. But this one here, we said it was true. At the end of the day, you indeed can say that 1/6 equals 5/30. That is sort of the point here, is to say that these are equivalent, and we proved that. Now, let's switch gears here, just slightly, nothing too major, but let's switch a little bit of our gears here and talk about proportions, since they are very closely related to ratios. And we're going to do so through a bit of an example. We're going to talk a little abstractly, and then I'll kind of use a more of a numeric application, or not application, but just represent it numerically and abstractly, algebraically. Two different ways of going about it. They both, and we'll see. We'll see what happens. So let's talk about things. Well, let's talk about something that you may already be quite familiar with. You may have seen this many times over, many times over. So let's start there. When you were in your fundamentals of math class, your general math classes leading up to where we are now in Algebra 1, you may have been taught the method of using cross products. And so I'll use that via a numeric example, cross products, where basically, you kind of did like that. You set that up. Some might even call this the butterfly wings, whatever, what have you. But basically, you ended up with, you took what I just circled here, 2 times 2. I took that, so 2 times 2. And then I'm saying it could be, is it 4 times 1? And the question is, is that true? And basically, you would work it out. 2 times 2, that is indeed 4. 4 times 1, that is indeed 4. You would end up saying that, yeah, these are true. And that's why, that works. It works. It works out to be true. And so you've been taught that. And that's, it's not necessarily wrong. It's just great to recognize the algorithm, I suppose, but let's talk about a little bit for a second here, the fundamental mathematics that are going on behind the scenes that make this commonly known algorithm, the cross products algorithm, indeed true. So let's talk about this idea. It really derives from the idea of common denominators, which is sort of what we did on the examples above, common denominators. And this is where I get a little abstract here, guys. But bear with me, bear with me. If I wanted to get a common denominator, now these, I'm using variables here to really illustrate the point, right? We're saying, basically, let me backtrack just a little bit here. We're saying that we took, let's call this A, and let's call this B, and let's call this C and D. And basically what we did is 2 times 2. So if this was the 2, we basically did A and D and B and C, and then they resulted in a true statement. And that's sort of what this says here. But how does that work? How does that trickery work? It's not just a magic trick. It comes from the idea of common denominators. So let us think about this here for a second. If I had no values to work with and just letters and variables, and I wanted to get a common denominator from it, what I would end up doing is multiplying, right, by, let's see, let me rewrite that here. I have b, all right, I want to get a common denominator. So on this side of the equation, I recognize I have d's, but I also need a b. And so in order to do that, I would need to multiply by a representation of 1, which would be b over b. Similarly over here, I have a b over here. I need a d in order to get common denominators. So I would multiply by a representation of 1, which in this case would be d over d. Doing so gets me a times d over b times d, and that would equal c times b over b times d. Okay, great. This is the process of getting I'll call it common denominator, CD. This is that process of getting common denominators. And that's great and all, but let's take it a step further. How do we get from this whole thing to this? This looks a lot simpler and cleaner to work with. This here looks like a bit of a, well, like I said, fractions are nightmare fuel. It looks like a bit of a nightmare, but it's not too bad, right? Understand that if I want to get rid of this fraction, I would end up basically inversing away the b and the d. So the b times d, I recognize that c times b is being divided by b times d, so I'm going to inverse that away by multiplying it. I'm going to inverse it away, and once I do what I do to one side, I have to do to both. So again, I will inverse it away. It's b times d, and basically what happens is these cancel, and you're left with a times d over 1 equals c times b over 1. And anything over 1, whether it's any number, 10 over 1, whatever, anything at all, 10 divided by 1 is 10. In other words, any number divided by 1 is itself, right? So this here would be 10. So in other words, I'll say ignore, because I know it will become itself, I can simply ignore writing this whole business, and so now I am left with a times d equals c times b. Again, very, very mathy way of basically saying that, yeah, your cross products algorithm will work. Very mathy way of going about saying that. Yeah, it'll work, but that's why it will work, because it comes from the application of mathematical law and properties, and it is a valid mathematical thing. This isn't just a magic butterfly trick. It has mathematical basis for why it works. So if when we work through these problems you simply just do this, great. But I just wanted to elaborate on why that works. Why that works. And this is why it works right here. This right here is why it works. Let's talk about a few more problems here. We're gonna now that you understand the basis, let's do a few examples. Let's use cross products there because it might be more simpler to you to do so. So let's try that. Let's try that here. Whoop, hold on. There we go. There's that there. Okay, let's try that here. Let's see if it makes sense. So if I did my cross products, I would have, let's do 5 times 121 equals 11 times 55. Okay, all right. And when I do that, that becomes 605, and this becomes 605. So let's see, I'm getting the same number on both sides of the equation. So that means that this is true, that these are equivalent. This is valid to say that these are equivalent. Equivalent. Yes, they are. Because statement of truth, everything checks out. Nice, lovely. Let's try the next one here. 21 and 36, 21 and 36. So if I do that, I would get 21 times 36 equals 63 times 9. If I work all that out, basically, what I would get is 756. I do that out, right? I might do the math right. So what that would become, if I times these together, that would end up being 567. Wait a minute here. You should be having some alarm bells going off here. This here, there's nothing further we can do. This here, there's nothing further we can do. But these are completely different numbers. So it is false. This is a false statement of truth. Therefore, they are not equivalent. Not equivalent. All right. Let us try another one. See, it may be difficult. It may be difficult to see 21 over 9 and 63 over 36. It may be difficult to see that immediately right away, but when we do the cross multiplication and we end up with, each these here, it's much more clear to see. All right, let's try another example here. We got a few more. Hold on a second. There we go. We got a few. I don't want to go too far yet. Okay, we got a few more here. So let's try. Let's work our magic butterfly cross multiply wizardry here. Okay, let's see here. Cross multiply magic butterfly 17 times 80. Okay, that equals, let's see, 16 times 102. The question becomes, okay, are they equal? That is the question. Are they equal? Let's see here. 17 times 80, if I did that, I would end up with 3060. Okay, and if I did 102 times 16, that would end up being 1632. Wait a minute. Alarm bells, once again. Nothing further we can do, nothing further we can do. This is a false statement, guys. This is not a statement of truth. These are not equivalents. Not equiv not equivalents. Okay, I am justifying this via cross products. Let's try another one here, just to get a real good feel. I hope we're getting an intuitive sense, or not intuitive, but just a better sense now of how we can use these things. Let's see here. Let's see here. So if I do once again, I can do across. What was that number there? It's a 369. Okay. So 369 equals, let's do 3 times 246. Let's see, if I do the math here, the multiplication here, this ends up being 738. And if I do the math here, that ends up being 738. Okay, again, nothing further we can do, nothing further we can do, but this time they are the same number. It is true that these are indeed equivalent. Now, here's a question that you may ask yourself when you look at, for example, well, okay, you realize these are false. These are false. So inquiring minds may ask the question, okay, well, if they are false, how do I make them true? How do I make them true? Well, that requires changing up one of the numbers. Any one of the numbers, there's four numbers total given with two in a proportion, four numbers total. If you could change one of them, then you would be able to manipulate it in a way that would make it equivalent, a true statement. It may involve using variables to achieve that goal. And so that's what I have set up here, is to look at a couple proportions where basically what we're trying to do is determine the value. For example, here, we're trying to determine the value that would go in this ratio here, right? This x, we're trying to determine what that x would be. And in determining what that x would be, that would be the value that would make this ratio indeed equivalent to that ratio, this one here. Let's try it, guys. Same process, cross multiply, butterfly. I would get x times 5 equals 3 times 30. 5x equals, let's see, this one becomes 90, right? Is that right? Let's see here. No, no, wait, no. Oh, wait, why did I put 30? It's supposed to be 10. Yeah, okay. 3 times, that makes a lot more sense. Okay, 3 times 10, yeah, that's 30. Okay, let's see here. Divide 5, x equals 6. Okay, so what that means is basically, if I go back up here and put this 6 in place here, so 6 over 10. 6 over 10, is that equivalent to 3/5? Well, just like from earlier, when we found least common multiple, we would multiply this by 2, 2. So the question would become, are these equivalent? Let's see. 5 times 2 would be a denominator of 10. 3 times 2 would be numerator of 6. 6 over 10 equals 6 over 10. That's true. So what we're saying, that we did all this, we solved for x, we solved for the variable that would end up resulting in a statement of truth. just like before. See how this all ties in together? I'm hoping you do, guys, because this is some neat stuff that we got going on here. Let's try another one here, all right? Again, cross multiply, magic butterfly, end up getting, let's see here, I got 7 times x minus 2 equals, let's see, 2 times 14. All right, listen here, guys. This looks very similar. Actually, it is, in fact, distributive property time. Let's see, let me do that a little cleaner and neater here. One there and one there. Okay, great. So distribute that 7. It'd be 7x minus 14. This one would be 2 times 14. That's 28. All right, let's combine like terms via inverse operations. So in other words, remove this and move it over there. So plus 14. This becomes 7x equals 40, oh, 42. Okay, divide 7. Whoa, divide 7. X equals, once again, 6. Well, let's see, does that make sense? Let's prove it out. Whoa, okay, hold on. Sorry, there you go. Boom. There we go. Let's prove it out. Let's plug it in. Substitute, replace, etc., etc. Let's see here. If I put in 6 minus 2 over 14, and I'm setting it, I'm setting up a proportion, a ratio, which says 2 over 7. Okay, least common multiple here, I can pretty clearly see that I would need to multiply by this by a form of 1, which would be 2 over 2. Let's see here. Okay, this would be, if I do that there, that would be 14. And 2 over 2 would be 4. Okay, so now I got 4 over 14. But what does this become? I got some simplification to do here. 6 minus 2, that happens to be 4. And then this does not change, so 4 over 14. Wait a minute, these are equal to each other. 4 over 14 is indeed equal to 4 over 14. It's true. It is true. We have proven that the variable x is indeed 6. For when we substitute it in, it results in a statement of truth. All right, guys, makes a lot of sense here. Makes a lot of sense. Let's make even more sense here with a couple more examples. Let's see. Let's do cross these, cross these. What do you get? You get r times 40 equals 8 times 25. This becomes 40r equals 200. Divide 40, divide 40. R equals, let's see here, 5. There we go, 5. Now, again, substitute this 5 back in. So you would get 5 over 8 equals 25 over 40. Least common multiple would be 5 over 8 times 5 over 5. And then I'm saying, is it equal to 25 over 40? Well, let's see here. This would be 40, and then this would be 25. And then it's equal to 25 over 40. Oh yes, guys, it is true. It is true. They're equivalent. Thus, R is indeed 5. It is the value which makes these two ratios equivalent. Let's try one more here. I think we're starting to get comfortable, starting to get a feel for this stuff here, and it's exciting to be able to say. So again, cross, cross, I would end up with 12 times 3x plus 2 just like that, 2 times 30. Okay, again, distribute. I would get 36x plus 24 equals 60. Inverse or combine like terms via inversing. Both sides. Let's see, this becomes 36x equals 36. Whoops, 36 36, divide 36, boom, 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 both sides. Looking pretty good here. This is going to be x equals 1. X equals 1. Well, let's see here. Let's plug it in and prove it out here. There we go. Put that in there. I would get, let's see here. 3, oh wait, no. 3 times 1 plus 2 over 2 equals 30 over 12. All right, let's see here. Let me do let me simplify this first before I start manipulating denominators here. So 3 times 1 is 3 plus 2, that would be 5 over 2. Okay, now let's see if I can manipulate denominators and such. All right, let's see. To go from 2 to 12, the least common multiple would be 6. So I can go ahead and multiply by 6 over 6. This would become, let's see, multiply across, 5 times 6, that would be 30. Multiply the bottoms, that would be 12 equals 30 over 12. Yes, these indeed are equivalent. These are the same numbers, thus they are equivalent. Thus it is true that x is the value which makes this whole thing possible. So we're getting a good feel for this. We're on the right path. We're getting a good sense of things. Now I'm going to throw some other, just take it up just a little bit more of a notch here. Maybe get some, as I said before, this has a lot of applications out there in life. We use this a lot out there in life, and so let's get a sense of how this might work in the real world. All right, so I'm just going to throw just a little bit more at you on this stuff here. But like I said, we're doing pretty good so far. We've got a really good sense of things. But let's talk about, let's define some more terminology that will be helpful for us when we start to do real world applications. So ratios again are two values related to one another. There's a relation between them. They have, generally speaking, well, ratios in their purest sense. Let me see if I have some writing space here. Let's see, I don't have a lot. So let's say ratios in their most pure sense relate, let's see, two numbers that are about the same thing. So you could say 2 to 3, and you can make the comparison that's like 2 cups of sugar as it relates to, or sugar as it relates to 3 cups of sugar. In other words, same units. These are this words here, cups of sugar, next to the number here, the number value would indicate that these are units of these numbers here. So a ratio in the most pure sense is relating values which have the same units. Now here's where things may differ. Here, yeah, so I can have a ratio in, I said before, the other one, purest sense. I can have a ratio, maybe not so much in the purest sense, but a ratio nonetheless. And this ratio may have two measurements with different units. Okay, it is possible. In fact, there's a lot of things out there where that is the case, right? And that would be called a rate. For example, a price of $15 per song. So for example, if albums typically may have about 10 songs, and they may typically cost about $15. Okay, so you would say that you would, that's how they're related. There you have a price to pay, and you can sort of equate that to a price that you pay per song. So that would be the rate. You have $15 for 10, right? Dollars for song, right? That's sort of how it would work there. A rate tells us how many of one item is being compared to one of another, and that is called a unit rate. So let me do that real quick. 15 over 10. Okay, that becomes, if I were to basically, let's see, 15 divided by 10. What is that? That is, let's see here. It's 1.5, or you could say also 3 halves, or 3, yeah, you could say 1.5, sure. 1.5. So what I'm saying here with unit rate is basically the cost for each one song. So the cost for each one song is $1.50. Cost per one song, right? Everything per one of something, that's a unit rate. A unit rate. So in this case, you would say the unit rate of, the cost of a song is $1.50. Anyways, there's sort of that. Let's talk about, let's see, a rate called a, there are these things, oh, like with maps and factories, when you build things out, you prototype things out, there's this rate that is often called a scale, and it is used to make a scale model of something. Like I said, a map is a good application of this. Things that you may build in a factory that you prototype are really good examples of scale models. And these things are constructed because it may be that the actual thing or is simply far too small or far too large to either work with or build to actual size. So you want to build a scale model that you can easily sort of work with and make inferences from as it relates to the actual size of things. So understanding that is going to help us out with these next series of problems here. Just a couple here, and not too bad here. But let's talk about something here as it relates to maybe a retail store opening sort of situation. We got stores, they're opening here. Let's talk about this here. So, well, let's read it here. In the past 2 years, a retailer has opened 232 stores. So I'm getting a sense here that there are 2 years, and that is related to 232 stores. I'm getting a sense right away. Oh, in fact, if that rate, stores per year, it even sort of tells me here, stores per year. If that remains constant, right, if that holds true going into the future, how many stores will be open in, say, in 3 years' time? So it might be a good idea to figure this out by setting up a proportion. So let's see, I'm seeing a relationship here between 232 stores, and it is related to the number of years, so 2 years in fact. And let's see here, as I said earlier, I want to, if I'm setting a proportion correctly, I want to have this other ratio such that the denominator units of one are lined up with the denominator units of another, so forth. I don't want to be saying that these are years and these are years. I want to be saying that these are years. So I want to put maybe a measurement of years here. Let's see here. How many years stores will be open in 3 years? 3 years is what it says. So I can put right here, 3 years. And the question is, how many stores will be open? Well, let's see. I don't know. That's what I want to know. So I'll say X number of stores. So this sort of closely models what we did not too long ago, except now we're dealing with units. And that is the real key difference maker. We're putting it into real world context by associating units to these otherwise abstract values and variables. Steps are the same though. Steps are the same. Let's do cross multiply and see what comes up. So if I do that, I will have, so one note here before I get going. You can sort of imagine that these units, that there's sort of like a multiplication happening between the, I'll call it, well, here, variable, but also coefficient, right? You can sort of imagine, actually, it's not imagine it is the case that they are being multiplied, right? This is like saying 3y, 3 years, right? That's like saying 3y. So when I write this here, do not be confused by what I'm writing here. I'm saying that, let's see if I'm doing the cross multiply this way first. Let's see, I'm saying that x times the number of stores times 2, right? There are 2 there, times years. Okay, if I do the cross multiplication, that's what ends up, right? These two are being multiplied, these two are being multiplied. There's 4 things in total being multiplied. Okay, great. Same thing here, 2 things here, 2 things here. So when I do the crossing, I should get 4 items being multiplied together. So 232 times stores times 3 times years. Now this may look a little intimidating, maybe daunting perhaps, like, whoa, I'm working with all sorts of crazy stuff here. But again, don't be too taken aback by what you're seeing here. You can just imagine that these are variables. If it's difficult for you to envision the full word, you can just imagine these are variables, right? But the steps are the same. The steps of solving for x, and that's what we're trying to do. The number of stores, which happens to be represented by x here. So what I would end up wanting to do is basically the same as if I were solving any other equation. I want to get x all by itself. All by itself. Well, what's happening to x right now? It's being multiplied by this concept of stores. It's being multiplied by this number of 2, and it's being multiplied by this concept of years. So I want to inverse what's happening to this x. What's happening to this x again? They're being multiplied, so I want to divide by this concept of stores multiplied by this concept of 2 multiplied by this concept of years. I want to essentially cancel all of these out and leave behind just a single x. That's really what I want to do. So let's do that. If I inverse that off this side, I got to do the same to both sides here. So I would have a concept here of stores times 2 times years. Okay, let's see here. Well, let's see. These would cancel. These would cancel, right? And now I'm just left with numbers here. So let's sort of clean things up a little bit here. I got x equals 232 times 3 over 2, which then further becomes x equals 696. That's what this is, 696, divided by 2, which further, when you do that division, that becomes 348. So 348. X happens to be 348. Well, that's what this has all led me to, right? This is now 348 stores. 348 stores. And if I went through the process of finding a common multiple, common denominator, I would indeed get these to be true. I'm sort of running out of space, so I'm not going to, well, maybe I should. You know what? Let's do that. Why not? So I'm going to clear some space here. Hopefully we remember all the steps that we're taking here. Okay, I'm going to clear some space. Why not? Let's do that. Okay, so we're saying x equals 348. 348. All right, so here we go. We're saying that x equals 348. Now, for the purposes of getting numeric values, I'm going to sort of ignore the units in this case. Again, I just want to see if the ratios hold true. So let's see, what I can do here is, let's see, if I do, here's my number 2 and 3. Let's see, 2, 4, 6, and this is 3, 6. So I need to basically, at my second listing here, I got my 6, and my third listing here, I got my 6. So basically, I would need to, the common multiple is 6, but in order to get to 6, I need to manipulate both of these independently. So it took me 3 places to get to 6, with starting at 2, and it took me 2 places to get to 6, starting at 3. So I can do that here, and again, I'm gonna disconsider the units when I sort of do this here. Okay, so let's see, 232 times 3, if I got my math right, will come out to be 696 over 2. All right, and then this here, 348, or no, wait, no, 348 times 2, that's what that is. 348 times 2 is 696 over 6. Wait, 3 times 2. And this is also 3 times 2. This is actually 6. Okay, and then I can further do that. I can simplify this further to say that, 6 divided by 696 happens to be 116. 116. They do, in fact, equal each other. It is true. So when we're saying x is 348 stores, we get a statement of truth that says 116 is equal to 116. It's equivalent. Thus, it is true that the number of stores that will open in 3 years is 348. Pretty neat, guys. Pretty neat. Pretty neat. And real world, too. This is real world. Listen, we're saying that we're basically growing by 116 stores each year. That's real life right there. Okay. And here's another one. Here's more along the lines of what you may work with as it pertains to scale models and scale drawings. And in this case here, we have a trail on a map, and we have a scale on a map. And what is the actual length? Now, here I'm seeing miles, and miles is, I can't draw a map that is quite literally 10 miles. That there's just no paper out there that even goes that far in length. So the applicability of scale drawings is very clear and apparent here, and using it is more workable. It's just not convenient for me to be working on maps that are 10 miles in length. Anyways, here, let's see. Let's try to set something up here. Well, it pretty clearly gives me how these are related. It's pretty clearly up front telling me that there are 3 inches, and it relates to this idea of 10 miles. Now let me just interject here and say that as it pertains to scales and scale models, that I just want to reiterate here, the 10 miles is the actual distance of this trail here, this Ramses Cascade Trail. These 3 inches is the scale. This 3 inches, we can represent this on a piece of paper, 3 inches, and we can say that those 3 inches represent 10 miles. We can draw 3 inches on a piece of paper, on a map. We can work with 3 inches fairly conveniently as opposed to 10 whole miles. So I just want to point that out. And let's see, if I'm setting up a proportion, I need something else on this side. Let's see, I've got my fraction line here. I need at least one more thing in order to start sort of figuring out what is the actual length of the trail. What is the actual length of the trail? Well, it's telling me whatever it's asking me is generally what I don't know. So what is the actual length? Well, let's see, if I'm saying this is actual, then actual on my other one has to be on the bottom. So I can say this x and then miles. This is actual. And then I can say here, okay, now if this is what I don't know, then I must know this somewhere. And when I look here again, oh, I indeed do. 1.125 inches. 1.125 inches. And that there is the scale. The scale. Okay, makes sense. Makes sense now. Okay, I got things sort of situated correctly, properly set up now. It's just a matter of let's cross multiply once again. 3 in, so I'm gonna, just like in the last one, 3 times inches times x times miles equals 10 times miles times 1.125 times inches. Nice. So the goal here is to get x all by itself. I recognize the things that are happening to x is that it's being multiplied by 3 different things. Let's divide by those 3 different things in order to inverse it. So 3 times inches, so times inches times miles. Okay, I want to leave behind the x. So if I do all this, these cancel. Okay, and I'm left behind an x. Okay, that's exactly what I want, but I got to do it to both sides here. Don't forget. So let's see, 3 times inches times miles. All right, let's see here. Got a miles up here and a miles up here. I can cancel those. Inches here, I can cancel those. I'm left behind, or numbers are left behind here. So the 10 times, let's see, 1.125 divided by 3. This becomes 11.25 divided by 3. Or in other words, x equals, let me think about that. What is 3 divided by 11.25? That happens to be 3.75. 3.75. So I can go through the process of plugging this back in up here, and you should, but for the sake of time, I'm going to go ahead and tell you that this is indeed true. I've proved it already, but if you want, feel free to plug it in yourself and work through just like we did in the last one to prove equivalence. Always encouraged, but for the sake of time, I'll go ahead and say that when x is this, these two ratios do become true. So what I'm saying here is that the actual length of the trail is 3.75 miles. There we go. There I go, right there. Actual length of the trail is 3.7 miles when I'm saying that it's 1.125 inches. Anyways, that's sort of that. Now, we covered a lot of ground today. We talked about just ratios in their purest sense and how to determine equivalence based on leveraging the identity property of 1 and common denominators. We also talked about proportions and how to solve for an unknown, I guess, piece, I'll say, of the proportion, which makes the entirety of the proportion true. So I hope this has been of value to you. I hope you've learned something, and I hope this helps us along as we journey forth through to the next topics that lie ahead. So have a good day. I will see you next time. Take care, and thanks so much.